Hello friends and welcome to YouTube channel on Engineering Mathematics by Dr. Navneet. In this video lecture, we are going to discuss the second method for finding the inverse Laplace transformation, which is called as inverse Laplace transformation by second shifting theorem. So friends, already we know that in our previous video lecture, we already discussed that how to find the inverse Laplace transformation by standard results. So during that lecture, we discussed total 9 standard results for finding the inverse Laplace transformation. So let me revise all these results once again. So inverse Laplace transformation of 1 upon s minus a is e raised to at. Then inverse Laplace transformation of 1 upon s plus a is e raised to minus at. When minus is there, then power is plus. Where power here plus a is there, then power is minus. Then this is the standard result. Inverse Laplace transformation of 1 upon s is 1. Then inverse Laplace transformation of 1 upon s square plus a square is 1 upon a sine of at. Then if the middle sign in the denominator is minus, then we can write this as hyperbolic function. So if s is present in the numerator, then we can write this as cos of at. Again, if middle sign is minus, then we can write this as hyperbolic cos of at. Then inverse Laplace transformation of 1 upon s raised to n plus 1. So when this power of s is greater than 1, if power of s is 1, then we can apply this result number 3. If power of s is greater than 1, then we can apply this result number 8. So all these things we had already discussed in our previous video lecture. So in this video lecture, we are discussing the second method for finding the inverse Laplace transformation. So before going to this method, we know the second shifting theorem of the Laplace transformation. So this second shifting theorem says that Laplace transformation of e raised to plus at, Laplace transformation of e raised to plus at, then f of t is equal to, this is phi of s minus a. Whenever here plus is there, then this sign is minus. So again, if this is plus then minus, then this is minus, then we get here as sign plus, where the value of Laplace transformation of f of t is equal to, this is the value which is called as phi of s. So this is called as the second shifting theorem. Now for applying this second method for finding the inverse Laplace transformation, so this concept is only applicable to result number 4, 5, 6, 7 and 8. So only for these 5 results, so this second method is applicable. So now let me discuss this result one by one. So first result is inverse Laplace transformation of 1 upon s square plus a square is equal to 1 upon a into sine of at. So how to apply the shifting theorem? So for example, inverse Laplace transformation of 1 upon s minus b. So suppose this b its square plus a square. So we can write this as e raised to bt into inverse Laplace transformation of 1 upon s square plus a square. So because according to the shifting property, so we subtract constant a from parameter s, or we add a constant a to the parameter s. So now here b is subtracted from parameter s, so we can write this as e raised to bt. So because this is minus sign, so we can write this as e raised to bt into inverse Laplace transformation of 1 upon s square plus a square. So moreover, we can write this as e raised to bt. Then this is the standard result of sine term. So we can write this as 1 upon a into sine of at. So in this way, we apply the concept of inverse Laplace transformation for second shifting theorem. So this is for the fourth result. So if this middle sign is minus, then we can write this as e raised to plus bt. But here if we take the sign as plus bt, then this sign become minus of bt. So this is plus and this is minus. So that means if middle sign is minus, then we can take this as plus, and if middle sign is plus, then we can take this as minus. So in this way we apply the inverse Laplace transformation concept for this fourth result, which is based on the second shifting theorem. So now to discuss this thing, so let's take the example. So if we wish to find out the inverse Laplace transformation of 1 upon s minus 4 its square plus, suppose this is 16. Suppose this is 16. So we can write this as, e raised to 4t into inverse Laplace transformation of 1 upon s square plus 16. So here we write e raised to plus 4t because 4 is subtracted from the parameter s according to the shifting theorem. So a is subtracted from parameter s. We can write this as e raised to plus 80 into f of t. So into Laplace transformation of inverse Laplace transformation of 1 upon s square plus 16. So we can write this as e raised to 4t. Then if we compare this with the result number 4, then we can write this as 1 upon 4 into sine of 4t. So now here we use the sign minus in between s and a. So one more example. So if we wish to find out the inverse Laplace transformation of 1 upon s plus, suppose this is 3 its square plus, suppose this is 25. So then here 3 is added to the parameter s. That means we can write this as e raised to minus 3t. So because 3 is in between s and 3, plus sign is there. So whenever plus sign is there, so we can write this as e raised to minus 80. So that's why this is e raised to minus 3t into inverse Laplace transformation of 1 upon s square plus 25. Now for finding the inverse Laplace transformation of this term, use result number 4 where the value of a is 5. So we can write this as e raised to minus 3t into 1 upon 5 into sine of 5t. So in this way we apply the concept of inverse Laplace transformation to result number 4 with the help of shifting theorem. So now let's discuss how to apply the second shifting theorem for inverse Laplace transformation for result number of 5. So now let's apply this result number for result number 5. So now for result number 5, again concept is very much same, only sign between two terms in the denominator is minus. So we can write this as inverse Laplace transformation of 1 upon, so this is s minus b its square plus a square is equal to. So now we can apply this concept. So we can write this sign as minus. If this sign is minus, then we can apply result number 5. Result number 5. So we can write this as e raised to bt into inverse Laplace transformation of 1 upon s square minus a square. So which is equal to e raised to bt into, this is 1 upon a into sine h of 80. So because of this s square minus a square, so after comparing with this result, we get this as 1 upon a sine h of 80. So this is the way where we apply the concept of inverse Laplace transformation for second shifting theorem. So now here we take minus sign. So if we take this sign as plus, then so this is the plus sign when in between s minus b is minus, so this is plus, and if we take plus, then this become minus. Similarly, so here we get this plus and this is minus. So now to understand this concept, let's take the example. So for example, inverse Laplace transformation of 1 upon s minus 2 its square, then minus, suppose this is minus 16. So to find out its inverse Laplace transformation, so we can write this as, so now here observe that 2 is subtracted from the parameter s. So according to this second shifting theorem, so a is subtracted from parameter s, so we can write this as e raised to 80. So that means this is e raised to 2t. Because of this minus sign, power is plus, into this is inverse Laplace transformation of 1 upon s square minus 16. So we can easily write this as e raised to 2t. Then this is the standard result of 1 upon a, which is 1 upon 4 into sine h of 4t. Because of this middle sign minus, we use the hyperbolic sine function concept. Now again, inverse Laplace transformation of 1 upon, suppose this is s plus 4 its square minus, suppose this is 25. So now to this example and this example, what is the difference between these two examples? So here we take plus 2, here we take minus 2, and here we take plus 4. That means we can again apply the concept of second shifting theorem. 4 constant is added to the parameter s, so we can write this as e raised to minus 4t into, this is inverse Laplace transformation of 1 upon s square minus 25. So which is equal to e raised to minus 4t, and this is the standard result for a hyperbolic sine function, so which is 1 upon 5 into sine h of 5t, because value of a is 5 square is 25. So in this way we apply the concept of inverse Laplace transformation by second shifting theorem to result number 4 and 5. Now let's discuss for result number 6. So now this is very simple technique, so only remember the concept of second shifting theorem and apply it in a reverse manner. So now we will discuss about this result number 6. Suppose if we wish to find out the inverse Laplace transformation of, this is s minus b upon s minus b its square, then this is plus, suppose this is a square. Whenever so step up term is there, that means when b is subtracted from the parameter s, so this parameter s is present, so this parameter s is present in numerator as well as in denominator. So here we can write this as s minus b. So here b is subtracted from the parameter s, so we can write this as e raised to bt into inverse Laplace transformation of, this is s upon s square plus a square. So we can easily write this as e raised to bt as it is. Then this is the standard result of cos of 80. So we can write this as cos of 80. So now here we take sign as minus between parameter and constant. So we may write this as inverse Laplace transformation of s plus b upon s plus b its square plus a square, which is equal to. Now here we subtracted constant b from parameter s. Now here we added constant b to the parameter s. So we can write this as e raised to minus bt according to the first shifting theorem into, this is inverse Laplace transformation of s upon s square plus a square, which is e raised to minus bt into cos of 80. So in simple word, when we add any constant term to the parameter s, then we write this as e raised to minus bt. When we subtract constant from parameter s, then we write this as plus e raised to bt. That means e raised to plus bt. So now to understand this concept, take the first example. Suppose if we wish to find out the inverse Laplace transformation of s minus 2 upon, this is s minus 2 its square plus, this is 9. Suppose this is 9. So then according to the second shifting theorem for inverse Laplace transformation, we can write this as e raised to plus 2t, because constant 2 is added to the parameter s. So we can write this as e raised to 2t into inverse Laplace transformation of s upon, this is s square plus 9. So now again this is of the type s upon s square plus a square, which is cos of 80, where the value of a is 3. 3 square is 9. So we can easily write this as e raised to 2t into, this is cos of 3t. So this is very simple example. Now let's take one more example. Suppose inverse Laplace transformation of s plus 2 upon this is s plus 2 its square plus 9, and we wish to find out its inverse Laplace transformation. So now here observe that if we put a bracket here, then constant a is added to the parameter s, so we can write this as e raised to minus 2t. Because here plus is there, then we can write this as minus, then into inverse Laplace transformation of s upon s square plus 9. So we can write remaining term in this way. So which is equal to e raised to minus 2t, then this is the standard result of cos of 80. So we can write this as cos of 3t, where the value of a is 3. So this is very simple result where we apply the concept of inverse Laplace transformation to second shifting theorem. So this is the result number 6. So now what is the difference between result number 6 and 7? Only denominator sign is minus. So if we put here minus sign, so if we change this sign as minus, then this sign become minus, and here we get this as cos h of 80. So this is the only change. Again here if we put minus sign, so then here again we get this sign as minus, and here we get this as cos h of 80. Instead of cos term we get hyperbolic cos function if we put minus sign in between these two terms. So again same thing here, if we put minus sign here, so then this sign become minus, then this is cos of 3t become cos h of 3t. Similarly, if we put minus sign between this in between these two terms in the denominator, so we get here as minus sign, same concept is there, and here we get this as cos h of 3t. So friends, in this way we apply the concept of inverse Laplace transformation by second shifting theorem to result number 4, 5, 6 and 7. Now let's discuss result number 8. So now let's discuss result number 8. Again this result number 8 is simple, so we can easily solve example based on this result number 8. So now take the simple example. So now example is, so for example inverse Laplace transformation of 1 upon s minus this is b raised to n plus 1. So here we subtracted constant term b from the parameter s. So to understand this concept, so we can write this as 1 upon n factorial into, no, so we can write this as e raised to bt into inverse Laplace transformation of 1 upon s raised to n plus 1, which is e raised to bt into 1 upon n factorial t raised to n. So simple. So constant b is subtracted from the parameter a. It may possible that we can add constant to the parameter s. So we can write this as s plus b raised to n plus 1. So if plus is there in between these two terms, then we can write this as e raised to minus bt into inverse Laplace transformation of 1 upon s raised to n plus 1, which is e raised to minus bt into 1 upon n factorial into t raised to n. So in this way we can easily apply the concept of inverse Laplace transformation by second shifting theorem. So this is all about the theory parts which is related to this method number 2. Now let's take some example based on this second method. So now let's discuss the example. Your doubts will get clear. So for example, find the inverse Laplace transformation of s upon s minus 3 raised to 5. So take the second example. Now friends, observe that if we take the inverse Laplace transformation of this term s upon s minus 3 raised to 5, then here denominator is in our standard form. So this is the type result number 8. 3 is constant 3 subtracted from the parameter s. So we can easily apply the second shifting theorem. But in numerator also s parameter is present. So to apply the second shifting theorem, we have to adjust the term in such a way that 3 will get subtracted from numerator as well as denominator term from the parameter s. So we can adjust this term as inverse Laplace transformation of denominator term is s minus 3 raised to 5. So numerator only s term is there. So we can write this as s minus 3. So we are subtracted 3 from the parameter s. So we can add 3 so that we get original term as it is. But after writing this as s minus 3, we can apply the concept of second shifting theorem. Now if we apply the second shifting theorem concept, then we get this as inverse Laplace transformation of s minus 3 upon s minus 3 raised to 5 first term, then 3 is constant, inverse Laplace transformation of 1 upon s minus 3 raised to 5. So from this step we write this step because of the linearity property of the inverse Laplace transformation. So we may put here bracket. Now here one term will get cancelled, so we can write this as inverse Laplace transformation of 1 upon s minus 3 raised to 4. Again this is plus 3 into inverse Laplace transformation of 1 upon s minus 3 raised to 5. So here one term will get cancelled. So now observe that 3 is subtracted from the parameter s. So we can write this as e raised to plus 3t into this is inverse Laplace transformation of 1 upon s raised to 4. Then this is plus 3. Again this is e raised to 3t into inverse Laplace transformation of 1 upon s raised to 5. So this is simple. Now we get this as e raised to 3t as it is. Now this is the standard result, which is result number 8, s raised to n plus 1. That means value of n is 3. So we can write this as 1 upon 3 factorial into t cube. Similarly, plus 3 e raised to 3t. Then this is 1 upon 4 factorial into t raised to 4 after applying result number 8. So now this is the third example for understanding the second method for finding the inverse Laplace transformation by shifting theorem. Now let's take the fourth example. Find inverse Laplace transformation of suppose this is 3s plus 1 upon this is s plus 1 raised to 4. So s plus 1 raised to 4. Again same concept is there, only adjustment is there. So if we take the inverse Laplace transformation of 3s plus 1 upon s plus 1 raised to 4. Now denominator is in our standard form. This is our type s raised to n plus 1 where the value of n is 3. But here 1 is added to the parameter s. So we can apply the concept of second shifting theorem. But here s is already present in the numerator also. So adjust the numerator term in such a way that we get the value as s plus 1. So we can write this as inverse Laplace transformation of this is 3s plus 3. So we can write this as s plus 1 raised to 4. So now here we require the value of s plus 1. So we can write this as 3s plus 3. So now here we require already only 1 is there and we write this as 3. So we can write this as minus 4. So that this is minus 4 and this become minus 1. So no. Right? So this become minus 1. So this is after adding this, if we take this as minus 4, then we get minus 1 answer. But actually we require plus 1 answer. So that's why we write this as minus 2. So 3 and minus 2, we get this as 1. So now in this way we can adjust the term. So if we adjust this term, then we get this as inverse Laplace transformation of 3 into s plus 1 minus 2 divided by s plus 1 raised to 4. So here in denominator we get s plus 1, that's why we adjust the numerator also in terms of s plus 1 terms, so that we can apply the concept of second shifting theorem. So now next step is, here we can write this as 3 is constant, then this is inverse Laplace transformation of one term will get cancelled. So I will write here. So we can write this as 3 into inverse Laplace transformation of one term will get cancelled. This is 1 upon s plus 1 its cube minus 2 is constant outside the inverse Laplace transformation, and this is 1 upon s plus 1 raised to 4, so that we get this as 3 into 1 is added to the parameter s, so we can write this as e raised to t into inverse Laplace transformation of 1 upon s cube, then this is minus 2 e raised to t inverse Laplace transformation of 1 upon s raised to 4. So we can easily apply the concept of second shifting theorem. Whenever some constant is either added to the parameter s or subtracted from the parameter s. So we can write this as 3 e raised to t, then here this is our type inverse Laplace transformation of 1 upon s raised to n plus 1, where the value of n plus 1 is 3, so n is equal to 2, so we can write this as 1 upon 2 factorial into t square minus 2, then this is e raised to t, then here s raised to 4, so value of n plus 1 is 4, so value of n is 1, so we can write this value of n is 3, so we can write this as 1 upon 3 factorial, then this is t. Friends, I hope you people like this lecture, so thanks to one and all. Thank you.